All right, now we've got the mic. All right, so we didn't miss much. Counting, base 2, base 10, same pattern. We name the digits in base 10. This one here is like, assuming this is like, oh, that's decimal, right? We've got the ones, the tens, hundreds, thousands, and so on and so on and so on. And it really means, like with the example with like the money, like this number would be 1, 2, 3. I've got 1 100, 2 tens, and 3 ones. How much is that in total? 123. The same idea is there for decimal or binary, but we've got like the 1s, 2s, the 4s, the 8s, and so on. It goes up by multiples of 2. Multiples of the base. Multiples of the base, 1, 10, 100, 1,000, and so on. Multiples of the base, 1s, 2, 4, 8, and so on. If you want to know what the number is, you say like, well, how many, if this is the number, if I've got 1, 0, 0, I have, okay, so remember this is 1, 2, 4, 8. Can you see that over there? Good enough? Let's do this. How many 8s? I have 1 8 and 1 2. 8 plus 2, that's 10. That has the value of 10. It works the same way as decimal, but I realize like with decimal, because we're so used to it, we skip so many steps. Where with binary, like we feel the need to translate it to decimal to understand what it means, which is, you know, fair enough. But, you know, it works the same way. I know it's like, oh, with binary, there's extra steps. It's actually the same steps. It's just we like to think of things in decimal, which causes the extra steps. All right? So like base 10, and here's another example. 1, 1, 1, 1, 0, 1, 1. By the way, usually I'm going to read these numbers like left to right. In the same way if I said like 1, 2, 3 for the number 123. Right? I would do that. So note that I'm like reading it from most significant to least significant. Most significant means like the most important digit or bit, right? The 8. Why? Because it has the biggest magnitude. It's the most significant. That's what I mean by that. So if I have the number here, 1, 1, 1, 1, 0, 1, 1, well, I have 164. I have 132, I have 116, I have 18, I have 0 4s, 1 2, and 1 1. So that would be, so 2 to the 6, that's 64. So I have 1 times 2 to the 6, which you'll notice is 1, 2, 3, okay, 0, 1, 2, 3, 4, 5, 6. That's its place counting from 0. So this would be 0, 1, 2, 3. What's 2 to the 3? 8. Oh, that's the 8th. Yeah, it follows that pattern as well, just like decimal does. Right? 0, 1, 2. What's 10 to the 0 is 1. 10 to the 1 is 10. 10 to the 2 is 100, right? It always works like that. It's the same. If it feels like I'm beating a dead horse, good, that means you get it. But I want to make sure you really get this. It's the same. So if you add all this together, if I have 1 to the, well, okay, 1/64 plus 132 plus 116, 18, 0 4s, 1 2, and 1 1. Of course, adding the 0 4s is kind of useless, but I'm including it there for like clarity. You add those all together, what do we get? That number is 123. Neat, right? So the position here really matters. Have you ever counted to 31 on one hand? You can. It's easy. So count to 5 on your hand. Everyone put your hand up and count to 5. Start like this and count to 5. Count there. Don't just get to 5. Count. How many fingers am I holding up? Like what number is this? 4. What number is this? What number is this? It's 4. You're just like counting the number of fingers I've held up. But the thing is, I'm not making use of position at all. You can make use of position to count a lot higher on your hands because I have 0, 1, now watch this, 2. Wait, 2. It is. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. What did I do? I counted in binary. I made use of like which finger, the position of the finger matters. When I have like this, what do I have? Well, I have, okay, 0, okay, so 1, 2, 4, 8, 6. I have 1 16 and 1 4 and 1 1. That's 21. You can count a lot higher on one hand. You can count a hell of a lot higher on two hands if you count in binary. So like, well, like why? Well, it's because I'm making use of the information, like the context of where the ones are, the ones being my fingers, where are my fingers on my hand, also have meaning. They are digits. But I didn't want to call them digits because like they're bit, it's a whole thing. But yes, they are digits. Good, that's funny. And for everyone that didn't laugh, what's wrong with you? All right, so there you go. What number is that? That's 19. Why? Well, we have 16, 1 16, 1 2, and 1 1. 16, 17, 18, 19. Right? Isn't that neat? That's pretty cool. Now you can impress all your friends with this new magical ability you have. So we talked about base 10. And we talked about base 2. Do we have any questions about base 10 and base 2 at this stage? Perfect. Picking a number base is entirely arbitrary. Like, why did we pick 10? We have 10 fingers. We like 10s. Why base 2? Well, there's utility in base 2, especially in computing. But like, it's kind of like, I could have a base 3. I could have a base 72 if I wanted. I could have a base whatever. Some are more like, have more utility than others. But the base of the number system of like how we encode our numbers is, you know, it's arbitrary. We could do whatever we want. And here's another one that we often do use in computing called hexadecimal. Often we call it hex, but it's hexadecimal, where we actually have 16 unique symbols, right? So using a base larger than 10 is fine, but there's only 10 conventional numbers, so we need an additional like 6 numbers. Well, we're really creative and we just use some letters, right? So any symbol can be used. We just need a symbol to represent like 11. Well, we start with A. Why? Because. So if you were to count in hexadecimal, I would go, okay, 0, 1, 2, 3. And there's an ordering. There's a magnitude. As you go that way, there's more there. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. What comes after 9? 10. Well, how do we represent 10 with a single symbol? Well, in hex, unlike decimal where we needed 2 symbols, we had to restart at 0, right, and increment the next. In hex, we have a symbol, one symbol for 10. We say A. B, C, D, E, F. F means 15. Once I get down to, okay, C, D, E, F. F means 15. How do I get to 16? I want to represent the value 16. I'm out of symbols. What do? I restart at 0, increment the next. Because remember, there's leading zeros. Right? And like I said before, when you have a 1 and a 0, whenever you see like 1, 0, that's always the base. And why is it always the base? Well, this is the 1s, and then the next digit is always the base to the power of 1. And if you have one of those, it's going to be the base. It must be. Otherwise, you've done something wrong. So that's how we go. And like I was showing you, counting works the exact same way. 0, 1, yada, yada, 9. How do I represent 10? A. We don't write 1, 0. We write A. B, C, D, E, F. And then 10 comes after 15. Although it's not really 10, it's 1, 0. Right? So 1, 0 means 16. 1, 1 means 17. Why? We have 1 16 plus 1 1, that's 17. Eventually we get to FF, that's 255. So with two symbols, I can actually represent the number 255, which is kind of cool, right? What comes after FF? Well, okay, that would be like the value 256. How do I represent that? 100, right? Cool. Like binary, they don't really have names, but we can call these digit positions like the 1s, the 16, the 255s, the 4096s, and so on. Pardon? Yeah, it should be 6s. How many 256s? Yeah, you want to fix that one or no? I'll do it later if you don't, but good eye. What he brought up is the third digit shouldn't be 255, it should be 256. He's right. Because the biggest number I can represent with two symbols in hex, let me get rid of this. There's a couple of ways to demonstrate this, but consider like FF. That is the number 255. So what comes after that? 0, 0, 1. So that this digit must be 256. How many 256s? If I have 1, I have 256. Also, what is 16 to the power of 0, 1, 2? What's 16 to the power of 2? 256. Yeah. Someone quickly do what's 16 to the power of 3? Well, just look it up. Let's make sure. If I made one mistake, maybe I made another mistake. 4096. All right, well, that one got right. Cool. All right, cool. Like decimal and binary, hexadecimal numbers can be broken down to the sum of their positional values, if it wasn't obvious already. So if I have the number 7b, I have 7 16s plus 11 1s, where b means 11, because a is 10 and b is 11. So that would be 7. If I have 7 16s, well, that's 7 times 16. And if I have 11 1s plus 11 times 1, well, it's 11. That's 123. Yeah. Cool. Well, that's pretty neat, right? Any questions about hex before we move on? Surprised no one has any questions. I guess you all are experts at counting. I wouldn't have guessed it, but here we are. No questions? Everyone's happy? Okay, converting between number bases. So, okay, we've only talked about 3 bases. There's nothing stopping us from having base 5 or base 123 or whatever we want. It really doesn't matter. Usually what you would do is you'd add a little subscript to the number to specify the base if there is any potential ambiguity. Like if I had the number, like if I just, like after this conversation, we just talked about decimal, we just talked about binary, and we just talked about hex. If I wrote the number 101, what is the value of that number? And well, that depends. I had a number in my mind, I encoded it as 101, but you don't know how to decode that number. Is that a decimal number? Is that a binary number? Is it a base 16 number? That could be the number 101, or it could be the number 5, or it could be the number 257. You don't know. So if there's, like, look, in everyday life, we don't go around and mention the subscript in our numbers. We don't go around and write little, like, 10. That's how I would say that is a base 10 number. Okay, that's usually how we write it. If there's ambiguity, we write it. If there isn't, like if you get your bill, they're not tricking you with base 16 numbers, right? That's absurd. So when there's ambiguity, we'll specify. A lot of time in this course, we're going to be dealing with binary, and I'm not going to specify binary all the time. Usually you should figure it out from context. But if you're confused, if you have questions, raise your hand and ask, because I may have missed making it clearer. If this was like this, well, that's base 2. If it's base 2271, that's base 2271. that's ridiculous, but it would be that. That's what that means. So that's what I mean about like eliminating ambiguity, eliminating any uncertainty about what that value could actually be. Because remember, it's just an encoding. 101 has meaning if you know how to decode 101, right? So like I said, what's the number 10? Is it, is it base 1, 10? Well, not base 1. Is it 2, 10, whatever? So yeah, 10 base 10, subscript 10 means 10, subscript 2 means 2, subscript 16 means 16. And in computing, binary and hexadecimal though, if we're like talking about this really in like the context of computing, usually we would write like 0B10 to mean binary. Or if it's hex, you write 0x10. That means hex base 16. Cool? Cool. Raise your hand if you've ever seen this in your computer before when like playing around with Python in another language. Yeah. That's how you would like specify a binary number. Or a hex number. So it's often useful to convert numbers from one base to another base. And we've kind of already done this like from like binary to decimal or hex to decimal, right? We just need to know what the meaning of each digit is, multiply how many things of that position you have with its like magnitude, and just add them all up together, right? That's what we did to convert from like to decimal, right? So saying 120, okay, it's often used for numbers between bases since that is what is used in everyday life. We're used to using base 10. We're human, we've been using it since we were this big, our culture has been using it since it was this big. We know what we're doing in base 10. So yeah, saying 123 is a lot easier for us to understand than saying 1111011 base 2 or 7b base 16. Obviously, representing these numbers in that way with these encodings has value for us in certain contexts, several of which we will see as we carry on in the course. But when talking just about numbers, we like base 10, obviously. So, like I said though, an encoding is an encoding. They all mean the same thing. It just depends on what the value was encoded and how we decode it. For both the binary and hexadecimal bases, numbers were already converted to decimal, like I showed you. All you do is you take how many of each like magnitude, like the digits magnitude or the bits or positions, whatever. So we have 1, 2 to the 6 plus 1, 2 to the 5 plus 1, 2 to the 4 plus 1, 2 to the 3 plus 0, 2 to the 2 plus 1, and so on. You add them all together and there you go. When I took this version of the course, like 1/3 of my semester was converting numbers between bases. We're only going to have one topic on it, so don't worry. But like, I'm talking about this, I just like, oh man, what a wild day, wild ride that was. Anyways, and then 7b. How many, like, okay, I have 7, 16 to the 1s, plus 11, 16 to the 0s. Add them together, we get 123. Okay? We've already done this. That's how to convert from one base to what we're used to. In general, multiply the value of the digit in base 10 by the value of the base in base 10 to the power of its corresponding position. Blah, 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 blah. That's just a fancy, that's me describing what I just showed you. So, for example, given some number of n digits d in base b, you would follow this pattern. Okay? This is the pattern you use. So consider the number J204 in base 20. Here, J would be like 19. Okay? Why? Because if I went through the alphabet, that's where I would land to get to like 19, and then 20 would be 10, right? If that wasn't immediately clear to you, go back and read. So how would I do this calculation? Well, if I have 19, 20 to the 3s, that's 8 thousandths, if I have 19 8,000s plus 2 400s plus 0 20s plus 4 1s added together, I get 152,804. It's kind of neat, right? Like with 4 like symbols, I could represent a much bigger number. Obviously, because each position can have more things. Have you ever like played the game? I remember being like, this should be obvious to you, and if it's not, you're normal because it is like a brain teaser. But I remember it was like, if I said, let me just put it like this, right? If I had, give me an eraser. What are we doing for time? Oh, we're in great shape. You work at a factory, no, a warehouse, and you have to like store things, and you're hired to come up with like codes to represent all the different types of widgets you have in your storehouse. And for whatever reason, you're using a really old computer, and you are given only 4 positions to like encode your unique identifier for each widget type you can have in your factory or in your warehouse, right? So, you know, you like numbers, right? We like numbers. It's easy to do arithmetic on numbers. We like it. How many unique values, how many unique things, like these are supposed to be, how many possible unique identifiers, how many combinations of 4 base 10 digits can I have? Well, we have 0, 0, 0, 0, 0, 0, no, 1, 0, 0, 0, 2, 0, 0, 0, 3, 0, 0, and so on and so on and so on and so on, all the way till we get to 9, 9, 9, 9, right? And then, well, we're out of spots, right? So how do we do it? Well, you could do something like, so what would that mean? Well, that would be 1, 0, 0, 0, 0. But of course, we don't have this. We actually looped back over, meaning we can't represent more. So how many unique things can we represent? We can represent a total of 10,000. Why 10,000? Well, it was, obviously we had 9999, 9,999, but we also had 0, right? And 0 counts. Clear? Clear. But like if you're smart and you're like, wait, I could just use like letters of the alphabet. How many combinations are there, right? Well, first of all, consider like, okay, let's just try to really calculate how many different, let's go back to integers. Whoa, 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 whoa. Let's think just integers. If I'm dealing with integers, how many different values can I have in here? 10. How many in here? How many in here? How many in here? Right? And for those of you that don't remember your stats or combinatorics or whatever, it's like, so for every 10 of these, I have 10 of these, and for every one of those, I have 10 of those, and I have 10 of all the different combinations. How many? 10 times 10 times 10 times 10, that's 10,000, okay? Well now, if we do letters, how many different letters are there? 26. So now I actually have 26 times 26 times 26 times 26, or 26 to the 4, which was, what did you say it was?
This is 456,976.
406, that's a lot more than the 10,000 unique things. So if I use letters, I can actually represent more things. Why? Well, I had more options for each position. And if you want to get really fancy, we can make it 36 because we can use letters and numbers. So what's 36 to the power of 4?
1,679,000.
Right. So if we allow for more uniqueness in each position, obviously we get more total things. Obviously. Cool. All right, converting from decimal. So to convert a number from decimal to some arbitrary base, divide the number by b and keep the quotient q 0 and remainder r 0. I'm just going to show you the example. It's just, you can work through this to generalize it, but it's going to be easier to just follow the example. If I have the number 123, I divide it by 2. Okay? I have, what do I have left? I have 61 remainder 1. Okay? Divide what's left, the 61, the quotient. 61 divided by 2, what do I get? I get 30 remainder 1. I have 30 divided by 2, I have 15 remainder 0. 15 divided by 2 is 7 remainder 1, and so on. You just keep dividing it by the base, and as you go, like the remainder will help you generate the number. That's how you do it. It would also work for hex, right? 1, 2, 3 divided by 16, well, that's 7 remainder 11, or b, because we're dealing with hex. And then what's 7 divided by 16? Well, that's 0 remainder 7, so it's, 7b. That's how we do it. If, like I was showing you, converting between arbitrary bases, I'm not going to cover this. What I would recommend, if I gave you, like a test and said, convert a number from base 5 to base 11, right? You could get really fancy and go straight from 5 to 11, but don't do that. Just go from 5 to 10, then 10 to 11. It's going to be easier for everybody involved. But there is an exception where if there's a really nice trick when converting between bases when one is an even power of the other, which makes it really easy. Okay? And this is really cool. And this is why we often like to represent big binary numbers in hex, because it's very easy to convert between the two. And it's, less digits is nicer than more digits. Right? If I have an 8-bit number, and it's binary, an 8-bit binary number, I can always represent that in no more than 2 hexadecimal numbers, right? And 2 is a lot nicer than 8. So consider a binary in hexadecimal. 2 to the power of 4 is 16. Each group of 4 bits corresponds to a single hexadecimal digit. Let me show you what I mean. So if I take 1, 1, 1, 1, no, wait, 1, 1, 1, 1, 0, 1, 1. Okay, that's actually a 7-bit binary number. 1, 2, 3, 4, 5, 6, 7. But what's out front here? What's always out front? 0. Yes, good. Good. So, you take the least significant batch of 4, or you can start with the most significant batch of 4. You just need to take a batch of 4. But like starting at one end or the other. The reason I'm saying take the least significant is because you always have like infinite zeros growing that way. If I start here, you might get confused and go 1, 2, 3, 4, and then you're left with only 3 in the end. So take this 4. 1, 0, 1, 1. What number is that? Well, that's 8, 9, 10, 11. That's 11. Okay? And then I have 0, 1, 1, 1. What is that? Well, that's 4, 5, 6, 7. Oh, that's 7 and 11. Oh, that's 7b, right? Because we write 11 as b in hex. So a group of 4 bits, in fact, that's not a coincidence. A group of 4 bits can easily be represented as a single hex number. Think about it. How many you need? Okay, look, let's just, maybe I have it here. I'll just draw it out anyways. Okay, let me finish this thought before I go get ahead of myself. So take the least significant batch, 1, 0, 1, 1. Well, that's 11 in base 10, or b in base 16. You take the next one, well, that's 7. And then all you have to do is just combine them, and you're good to go. It works because any grouping of 4 bits can have 16 possible values, right? If you don't believe me, let's count. 0, 0, 0, 1. 0, 0, 1, 0, 0, 0, 1, 1. So notice with 2 bits, how many numbers how many different, 1, 2, 4. If we only consider one more, oops. Where'd I put it? Over there? Ah, man. I need a holster for my eraser. 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. How many is here? 1, 2, 3, 4, 5, 6, 7, 8. Interesting. Like, it's kind of neat. Like, I'm going to, like, pretend this doesn't exist. Okay? I've got all possible combinations of 3 bits. I'm going to repeat this pattern entirely. Okay? 0, 0, 0, 0. Nope. No, no. 0, 0, 0. 0, 0, 1, 0, 1, 0, 0, 1, 1. I'm running out of room. 1, 0, 0. I know you can't see this, but just pretend you can. 1, 0, 1, 1, 1, 0, 1, 1, 1. 1, 2, 3, 4, 5, 6, 7, 8. Perfect, right? I repeated the pattern. The pattern always repeats. But I've got that leading 1. Every time I add one more thing, I double the amount of things I can represent, which is neat, right? Every time, because remember, there's also 0, 0, 0, 0. This leading 0 is there. If I were to add, like now add another 1 here, I would have to repeat this whole pattern of 16 things where this is 1. Like every time I add another bit, I double, which is cool. Makes for nice, easy math. Questions about that? All right, so where was I going with this? Yes, so let's get rid of this. I have 16, like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16. Well, this corresponds to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. They might not be lined up. 1, 2, 3, 4, 4, 5, 6, 7, 8, 9, 10. What comes out? Oh, A, B, C, D, E, and then F is down here too, trust me, because you can't see it. The point is, there's a one-to-one mapping. There's no guessing. If I have 1, 0, 0, 0, well, that's obviously 8. So if I wanted to convert a binary number to hex, I could just take that number and immediately just convert it nicely to that. Yeah?
Doesn't A come after 9? Or
A come after 9? It is. Here's 9.
then you have a 10.
10. A. Ooh! Yep. That makes this fit better. Did everyone catch what he caught? I wrote 10. Foolish! There is no 10. There's only A. D, E, F. Good catch. My mistake. There we go. Much, much better. There's a nice mapping. Now there's a nice mapping. Before there wasn't. There was a magic 10. Any questions, questions, questions? It's really easy to convert. Obviously, like, I know that, like, in my head just now, in our head just now, we were like, oh, well, that's the number B. 1, 0, 1, that's 11, which means B. So I did do that thing where I went from 2 to 10 to 16. I know I did do that, but, like, I don't know, it just feels a lot easier when it's an even power of one thing. This would also be true if we had like a base 8 number. It would be really easy to convert, but I would only need 3 bits, groups of 3 bits to do it. Base 4 numbers would also work the same way too, but I only need 2 bits to represent those things. This works in general when one base is a nice even power of the other. Base 4 can be obtained by containing 2 bits from base 2. Base 8 can be obtained by combining 3 bits from base 2, 16, 4 bits from base 2. Base 16 can also be combined 2 base 4 bits, or digits, or whatever you want to call them. As long as those all line up, we're in great shape. Which is really neat, right? Like here's me counting in base 4. 0, 1, 2, 3, 1, 0, 1, 1, 1, 2, 1, and so on. But I can convert to base 8 really easily. And so on, and so on, and so on, and so on. Which is pretty neat. FYI. So any questions about swapping around number bases or anything? Bless you. Like I was saying before, it's really important for you to understand how we are encoding and representing numbers. The numbers, I mean, we could play a philosophical game of like, what is the number? Is it the number 101 or is it the meaning, right? Is it a more abstract idea or is it a quant? We could play that game fine. But the point I'm making is, what am I trying to convey and how did I represent what I'm trying to convey to you? These are separate things. They are. Whether you like it or not, the idea of a cat in my brain is not the same thing as me writing CAT. The encoding and the meaning are separate. And this is important. I mean, don't get me wrong, it's important to know about converting bases around because we're going to be doing some of this type of stuff. That is important in and of itself. But a big part of this is making sure we are aware that, like, and it's funny, there actually is a nuanced difference between like the meaning of the word data and information. Of course, I'm going to get it wrong. I bet I'm going to get it backwards or something. But like data is just like a statement. Like it's just like a number. But like what it means is like the information. So there actually is even a difference in like the wording we use in everyday life, by the way. We might not be thinking about it, but there is distinction in our vocabulary for this type of stuff. Questions, thoughts, concerns, comments, anything? Okay, perfect. How many of you have ever thought about counting like this much before in your life? I didn't. You did? You're weird. It's a compliment, though. Okay, Boolean logic. Raise your hand if you've ever heard of the idea of Boolean logic before. Of course you have, right? I'm saying much of the following will likely be a review. It better be a review. If any of what I'm about to, actually that's not true. The second half of this is probably going to be new, but you kind of already know it, but you never learned it explicitly. But most of the early stuff, you better know this already. It's just review. This topic is covered for completeness, but I'm going to keep it at a high level. So Boolean operators and operands. I'm going to make sure I've got a clear space here. So pardon me while I clear this off. First of all, let's make sure it's clear what I mean when I say operator. Now, operator is actually kind of a funny one. It usually is used to be like, okay, if I want to perform the operation of addition, okay, that's an operation. So I say like plus, that's the operator. That's the symbol that means like addition. And the operands are like 1 and 2. So if I perform that operation, I get 3. Operator, operands, right? You hopefully learned this at some point in your life, but it may have been a long time ago where these words were described to you. But like we usually deal with these things at a high enough level that we don't talk about them as operator and operands very often, but that's what they are. Boolean logic is a form of algebra that operates on Boolean values. Not like numbers, where addition works on like numbers, right? We're going to deal with Boolean values. And we all should probably know that Boolean value, like, how many unique values are there in integers? An infinite. There's a lot. How many unique values are there in Boolean? 2. True or false? Sometimes we write them as true, false. Sometimes we might go TF. Sometimes we might go 1, 0. Sometimes we might say like on, off. Might say high, low, high voltage, low voltage, 5 volts, ground. The point is I've got this like one or the other, okay? We'll use a lot of different words throughout this course depending on the context, but they all have value. They all have like the same meaning in the context of Boolean algebra, okay? Usually if I say on or off, which one do you think is true and which one's false? On's probably true. And if you didn't know that, well now you do. There's a lot of ways we can like write this. And I will be flip-flopping around all the time. These two different values, or states, are typically called true or false. And depending on the context, like I said, they might on, off, 1, 0, high voltage, low voltage, whatever. And within the algebra, the operands are these values. And they can take on one of two states. Okay, so it's easy. It's simpler than basic arithmetic, right? The operators act on these operands to produce a new Boolean value. Okay, so if I say true and false, operator, operand, what do I get? False. Don't get confused by missing a step. It's actually amusing isn't the right word. I laugh and cry at the same time whenever I have a test for 161 and I give them something like this and they get it wrong. And if you're looking at this and you're like, how could they possibly get it wrong? It's because I will explain to you exactly how someone can get it wrong. Okay, it's possible that the person has no idea what's going on, which is wild. But it's because they're always used to thinking of these operators in the context of a question. Like, am I wearing a hat? That is a question that gets evaluated to true or false. So like they can't, like this isn't even, this is a simplified version of that, but they can't see that this is a simplified version. They're like, this doesn't make any sense. It does make sense. It's just, it's a simplified version where I didn't have to say, is it sunny outside and is it raining, right? So true and false is false. This is an example of binary operator, one that takes two operands, but you are all likely familiar with a unary Boolean operator. Who wants to guess what that is and what that means? It only uses one, and what Boolean operator that I know Boolean, I'm not saying binary, I know it can sound confusing. What Boolean operator do I know you all know only acts on one operand? Not, right? So if you have not true, that's like a symbol for not. Sometimes they'll do it like that. Sometimes they'll do it like that. Squiggles are not. There's a lot of different things. You'll pick it up. What's not true? False. What's not false? True. So we have binary and unary Boolean operators. We can generalize. Like I said, I need a holster. We can generalize the Boolean operators, or the binary operators, to be like true and false and true. You can be like, well, this is like, we can make and work on 3, really, but really it's actually like working on it. It's just doing it twice, right? And this would be like true and false, well, that's false and true, well, that's still false, right? But the point is, like, sometimes you might see like and being applied to 3 operands, but that's just like a shorthand way of saying like, well, we're applying and multiple times to make it work. It really only ever works on 2. Okay, in this term, okay, if the terminology is throwing you off, remember, okay, this is like what I said, right? If the terminology is throwing you off, you're thinking too hard. Classic mistake of computer science students. Remember, computer scientists are stupid. If things get complicated, we've messed up somewhere. We can't deal with that type of stuff. So just remember, we're stupid. So, when in doubt, think dumber. Just the same thing with addition, right? 1 plus 2. Operands are the numbers, operator is addition. There are 3 basic Boolean operators. Not, this is the unary operator, only operates on a single operand and produces a single value. Given some Boolean value, we invert it. What do I mean by invert? Well, just flip it to the other one. There's only 2 binary values, so if it's true, make it false. If it's false, make it true. Like I said, we typically denote it like that or sometimes like that. This is commonly how we do it. Sometimes people write not. Sometimes we'll do tildes, whatever. There's a lot. it'll be kind of obvious because there's only 3 of them. And is a binary operator, it takes 2 operands, given a Boolean value, A and B, return true if both values are true, false otherwise. Denoted like that, typically, if you're writing this like as the Boolean algebra syntax. If you're doing it in Python, what do you usually write? You type A and D. If you're doing it in Java, what do you usually write? You do ampersand, right? What did you say? False. Who knows why he's wrong? What does double ampersand mean? Now, I'm being nasty because yes, it means and, but by the way, we'll end on this. Well, let me finish or. Or, we know what or is. 2 operands, single value, returns true if either of them are true, otherwise it's false. And we represent it as like this upside down V or like a U. If this sounds a lot like, raise your hand if you've ever dealt with like sets and set operations, like unions and intersects. If this sounds a lot like that, yep, correct. It does, because it's like the same freaking idea. In fact, I stole these from Wikipedia and just changed the symbols from intersect and union, right? It's the same thing, right? Cool. But the difference between, like in Java or C++, C#, C, and a lot of other high-level languages, there is, so in Python there is such thing as an ampersand, but it's bitwise and, as opposed to like and. And we'll actually learn a little bit about that later in the course. A single ampersand in Java means and. Double ampersand in Java and a lot of other languages is a special and that means short circuit and. So let's say I have a function. I'm not going to try to draw. There, that's my double ampersand. I know it's not. So this is some function that returns a Boolean. And here's another function that returns a Boolean, right? Now, some might argue this is bad programming style to begin with. Fair enough, right? But if this function returns false, do I care what this does? No. So double ampersand is short-circuited, meaning if we ever get to the situation where I know the result of this whole expression is false, don't waste your time. Imagine this is like an O n factorial thing. It's crazy. Yeah, you just saved yourself a hell of a lot of time. That's good. But it's also entirely possible that this function has some side effects or something where like even if I know this is false, this better still run. In that case, I would say just ampersand, where it guarantees that both sides run even if I know that the final result is false.
In that case, you should probably store them in their own values and then put them in the function.
Sure, fair enough. Or you shouldn't have side effects in your code anyways, because that's just not the best thing to do.
No, without side effects, they would do basically the same thing as the regular name.
It would really depend. But anyways, there is a difference, and I use you as my example. So thank you for that.